Hello,
No, 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 no.
hello, 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 hello. So, good morning, everyone. So, we will start today's session, which is extra session, and it's our last session also. So, this is Rahuldev Ghorai from Tiruvananthapuram School of Mathematics. So, we'll start today's session by starting with some differential equation, which we discussed in the last session also. So, we'll mainly little bit recall those things, and also we'll do some problems from the higher order linear differential equations, and at the end I would like to do some mean value theorem and Rolle's theorem, some problems on mean value theorems and Rolle's theorem, which I felt interesting. So that's how we will end today's session. There will be part 1 and part 2. Part 1 will be on differential equation, mainly higher order differential equation, particular solution, general solution, particular solution, complementary function, all those things. And then at the end it will be on mean value theorem differentiality for one variable itself. Okay. So let's begin with a differential equation, higher order linear differential equation, which we did yesterday. So if you see the homogeneous linear equation, how it looks like. Homogeneous linear equations. They look like this: yn, nth derivative of y, which is a function of x, yn minus 1. Yesterday also I did. I just recall some of these things and then we will start. That's why. So pnx of times y is equal to 0. Right hand side will be 0. Homogeneous linear equation of nth order. Right? Nth order. Degree is, it's 1. So it's linear. So degree will go on. Okay. So what you can observe here, if Rx is a solution, then any constant multiplication C is a constant from, let's say, any real number times Rx, this will be also a solution, right? Then this is also a solution of this one homogeneous linear differential equation. Okay, when I say homogeneous linear equation, means homogeneous linear differential equation. We are doing differential equation. Even though if I am not writing, you have to understand that. Okay. So the some few remarks I will say here. So that Rx, if it is Rx is a solution of the system of the equation 1, which is a homogeneous linear equation, then any constant, if you multiply any constant also, that will be also a solution, right? How? Because if Rx is a solution, then nth time derivative of R plus P1 times P1x time R nth derivative of n minus 1 derivative of R plus up to Pnx R is equal to 0, right? Now if you, what about Cr nth derivative of Cn, that will be C times, because C is a constant, it will come out, so it will be R in C times Rn. So similarly, if you have Cr n minus 1 derivative of Cr, that will be C will come out, it will be n minus 1. So that's how, if what you can show that Cr to nth derivative of CR plus P1x CR n minus 1 derivative plus up to Pnx CR, that will be equal to C times Rn plus P1x Rn minus 1 derivative of R plus up to Pnx times R. So that implies this is nothing but C times 0 because R is a solution. So that implies 0. So CR also a solution. That's what we can show also easily, that if R is a solution, then C times R will be also a solution of a homogeneous differential equation. So remember that it's a for a homogeneous linear differential equations. It's not true for non-homogeneous. Okay, you can take one very easy example and I can show that also. Okay, another remark is if you see Rx and Sx, if Rx and Sx are two solutions for one, or Sx R and S2 functions which satisfy the differential equation point wise, then what will happen, what you can show that Rx plus Sx will be also a solution. Okay, what does that imply? So can you say something? It's because I hope you have done vector spaces, right? Little about vector space, you know. I remember I did this vector space, some problem from vector space and all. Yeah, I will assume that you know vector space. What is vector space? So I just wanted to connect the vector space and differential equation a little bit. Okay, so as it is an extra class, so you can do something, some of those things. Vector space is if you recall vector space was a like abelian group with a linear structure is there. I mean, so abelian group with respect to plus, and you have a scalar multiplication, so closed under scalar multiplication. See that everything is happening here. Rx plus Sx is set of all functions, they make a vector space, right? And now you have a space. Let's say space is S, not S. Let's say W. V is a vector space which is set of all function, right? Set of all function. It's a vector space. V is a vector space, and W is the solutions of the differential equation 1. Okay, so then W is a subspace, or W is a vector space subspace of V, right? That's what you are getting. R, if you take two elements R and S from W, they mean if you take R belongs to W, that implies Rx, R is a function and Rx is a value mainly. Rx satisfy this one mainly, right? And then Cr will be belongs to W because Cr satisfies one. So that's how we can show that R and S belongs to W. Then R plus S belongs to also W. That's what we showed already. Already we have shown. So that's how W is a vector subspace or vector space also. So set of all solutions of the differential equation, I mean homogeneous linear differential equation, will be a solution for set of all solutions of the differential equation will make a vector space, will create a vector space or a vector subspace of a vector space which is a set of all functions, which consists of set of all functions. Okay, So that was a remark from the solution of the linear differential equation. Okay, homogeneous linear differential equations. Also, you can show that if this uh, if you have a solution, see if it's a nth or nth degree differential equation, sorry, nth order differential equation, then you will have solutions which involve n arbitrary constants, right? N arbitrary constants. So what will happen if you have nth differential equation? I mean, if you have yn, I mean, for one, the solution will look like c1 y1 plus c2 y2 plus up to cn yn. The solution will look like this: c1 c2 up to cn, and we'll say y1 y2 up to yn, they are linearly independent. We'll say it is linearly independent if the Wronskian of this is non-zero. So there was a question, so that's why I'm just making make sure that you can do. So that will be, as it's the nth order, so this will be a matrix. It will be a matrix of like this: y1 y1 1, I mean it's the first derivative of y1 up to nth derivative of y1, and y2 up to nth derivative of y. It will keep on going. It will be yn first derivative and yn nth derivative, right? This is a matrix. If the determinant of this matrix will be the Wronskian. So determinant, if it is non-zero, if w is not equal to 0, then y1 y2 up to yn is linearly independent. We will say linearly independent. Okay, so let us do an example to make sure that you understand. So this will be, this is a first one, one of your assignment question. So it is said that the functions, whether ask that x e to the power 4x e to the power minus 3x, whether they are linearly independent or not. So for that, what you do, you take the function, first function x, you write 4x to the minus 3x also. Then you take derivative of x, this will be 1. Second derivative will be 0. First derivative of e to the 4x will be 4 e to the power 4x. Second derivative of this will be 16 e to the power 4x. First derivative of e to the power minus 3x will be e to minus 3 times e to the power minus 3x. 9 times e to the power 3x. Right. So that is will be equal to, this is nothing but Wronskian of x e to the power 4x e to the power minus 3x. That is equal to this. So that implies you can write x time 4 times 9 will be 36 e to the power 7x, right? Plus 16 times 3 will be 48 e to the power 4x minus e to the power 3x will be e to the power x minus 1 times 9 e to the power 7x. Yes, 9 e to the power 7x. Seven x minus 16 e to the power x. What does that give you? Did you do any mistake? So it is a minus 3x, so nothing will be 7x, it will be x only. Okay, okay, yeah, yeah. So now it's okay. So this will be x time, what is 40, 36 plus 40, it will be 84. So 84x e to the power x minus, it is will be 7 e to the power x, so it will be minus of minus, so it will be plus 7 e to the power x. So can anyone say whether it is 0? Can it be 0? It can be a 0, but that's not always. So it is like 7. If you take 7 e to the power x, you take common, it will be 12x plus 1. So it is 0 only if x equal to minus 1 over 12. But that is not always, right? So it is not always 0. So it's not equal to 0 that you can write. So only if it is at one point is 0, that is not a problem. It has to be non, it has to, if it is 0, it has to be 0 for all x. So that's why we will write, you can say that this function is non-zero function, right? What is a non-zero function? The function which does not take 0 values for all the input. That's not happening here. I mean, that is happening here. So it is not taking 0 values for all x. So that's why it's a non-zero function. So we can say that x with our 4x, the minus 3x are linearly independent. Okay. So this was one of your assignment question, but the things are coming from the linear homogeneous differential equation, which is having the solution will have the nth, if it is the nth order, then solution will have n number of arbitrary constants. And if n, if you have n linearly differential, linearly independent solutions, then you have the Wronskian will be non-zero, and the vice versa. If Wronskian also non-zero, you can say that they are linearly independent. Okay. Okay. So one more thing is, you can show that the dimension of this vector space, the vector space we formed, like w, dimension of w will be n. That you can show that. Okay, that is easy. So you just check it. It's not only be, it won't be uh, useful for you maybe for this course, but yeah, no, if you know, it will be better. So you just check any other, any textbook, you will get it. So standard text will have dimension of w will be n. Dimension we told already, right? Dimension will be a like number of element in the basis. And what is basis? Basis is a linearly independent set which span the whole set, whole space. Okay. And mainly in this course, you are like you do you solve constant coefficients linear differential equation. Okay, you don't go beyond that. Although if it is having non-constant uh, non-constant coefficient, you make it, you transform it to constant coefficient and you solve it. Okay, so that's why knowing constant coefficient, knowing how to solve the constant coefficient differential equation is very useful. Okay, So the motivation behind solving, like how do you get, I yesterday I talked about auxiliary equations and all, okay? So how those things came into the picture. So mainly the next we will concern how to find the n linearly independent solutions. So there is no good method in general. So however, a technique which work in special cases where all constant are coefficient, so we can do something there. So what is that? So you can, if you have a naught times y, nth derivative of y, and it is keep on going, this is a general linear differential equation, let's say you have, then somehow if you look for the solution of the form e to the power lambda x, what will happen? This yn will be lambda n, it's not now nth derivative, it's nth power, it will be 8 times e to the power lambda x, and it will be like, I mean, y n, n minus 1 derivative of y will be lambda n minus 1 e to the power lambda x. Okay, we'll keep on going. So now from there what you get is lambda n. I assume that this type of solution exists. We'll check whether it exists. We can come to contradiction, or we can, like, we'll get something. Let's see what is happening there, like what we are getting. So lambda n, a naught lambda n plus, from here what you can get, then if y is equal to lambda x is a solution, and we know these are for any y which is e to the power lambda x, then these are like this. So if this is a solution, then what we get is a naught lambda n plus a1 lambda n minus 1 up to an times e to the power lambda x will be 0. What does that imply? That implies a naught lambda n plus a1 lambda n minus 1 plus up to an will be 0, because e to the power lambda x anyway is not 0, right? E to the power lambda x is never 0 unless x is converging to minus infinity and all. We only worry about the finite x, or I mean it's not infinity. Okay, that's why e to the power lambda x is never 0 in that sense. That's why a naught lambda n plus a1 lambda n minus 1 up to an will be 0. Now you know how to solve this, because a naught, a1, an, you know what are, like, what are those? I mean, so those are known to us. Let's say if you have n distinct real roots, if it is having n distinct real root, then those will be, let's say, r1, r2 up to rn. If they are n distinct real root, then you will have solutions like, what you can write, e to the power r1 x is also solution, right? Because we started with y is equal to the lambda x the solution, assuming so that, and the lambda value you are getting, lambda is equal to many, this is these are lambda values only. So e to the power r1 x or e to the power r2 x, e to the power rn x, all are uh, solutions. All of these are solutions, and one can check that these are linearly independent also. Linearly independent solution, you have linearly independent solution, and you can show that c1 r1x plus c2 r2x, so any solution, sorry, r2x, cn rnx, any solution will be of the form this, because I said, right, this is a set of n number of solutions which are linearly independent, and you know any uh, any solution will be in the n-dimensional vector space, because the space where the solution belong is of dimension n. Because I said so that we haven't justify, but you can check it. It's you can check any other any textbook. So dimension will be n, and you have n number of linearly independent solutions. So e to the power r1 x rix, all I for I belongs to n1, it will be in the W vector space W, right? W is the set of all solutions of the homogeneous linear differential equation. And then what is the meaning of that? So that they are linearly independent and this belongs to W. So any W, any element in W will be of the form this. And any element of W are what? The W from the construction W is the set of all solutions. So any solution will look like this. See, you got very easily, or you can just you have justified what is auxiliary equation and why you write this c1 e to the power r1x plus e to the power r2x and all. I mean, for example, y2 minus 5y1 plus 6y is equal to 0. You had this type of differential equation. Why you wrote m square minus 5m plus 6 equal to 0, then m is equal to 2 and 3, that from here you will easily get. And then y you used to wrote c1 e to the power 2x plus c2 e to the power 3x. Why you used to write that? That's the reason here. So in this case, the solution space of this differential equation, linear differential homogeneous linear differential equation, will be of dimension 2, and you have this e to the power x, e to the power 2x and e to the power 3x. They are linearly independent, so any solution will look like some, it will vary only with the constant coefficient, some arbitrary constants. See, any solution will look like that. That's why we will write that solution is this, and where c1 c2 you vary, whatever c1 c2 you give, I will give one another. So you give one c1 c2, I will give one solution. So there is this infinitely many solution for different c1 c2 value. Okay. Yes, that was one one thing. So now I will justify for repeated root. Let's not take it for nth degree, sorry, nth order differential equation. So we'll take, let's say, second order differential equation of which will have a repeated root. Then why we don't write, if you have repeated root, let's say m is equal to 2 and 2, then why don't you write c1 e to the power 2x plus c2 e to the power 2x itself? So one reason is it will become c1 plus c2, which is another constant you can write, and this is kind of one constant. But still, why we don't write like this? What's the problem? One, if it's a one constant also, what is the problem? You can say that maybe the solution should have n number of arbitrary constant, but why is that is also what is that is the question? Why is that so? Okay. So in order to make sure that this won't be like this, let's analyze this from the vector space idea. I mean, from the concept of vector spaces. Okay. Let's say you have like this for y is equal to 0. This can be, this cannot, can this can be. It is a differential equation which is linear, homogeneous. Okay. I will show that this auxiliary equation will be m square minus 4m plus 4 is equal to 0. That implies m minus 2 whole square is equal to 0. So roots are 2 and 2. I mean, repeated root. 2 is coming twice. Okay. So in these cases, what will happen? The solution is e to the power 2x only. I mean e to the power 2x and e to the 2x. That does not make sense. Only one e to the power 2x, right? And these two are what? They are linearly dependent. They are not the same. So they have to be linearly dependent. So they are not linearly independent. So that's why we cannot write any solution will be looking like e to the power 2x, because we are writing general solution for this homogeneous differential equation. So we cannot write c1 plus c2 to the power 2x. Any solution won't be of the form this, because they're not linearly independent. So when you have linearly independent, these are not linearly independent. When you generate the vectors, generates the space using this e to the power 2x, that won't be the whole space, because the whole dimension of the whole space is 2, and here you have only one element which is e to the power 2x. So what in that scenario you do, you can check that x times e to the power x, that also whether it becomes solution or not. I mean, you can show that for x times e to the power x, we will now check that x e to the power 2x, let's say y is equal to x e to the 2x, then y, first derivative of y will be e to the power 2x, y, sorry, e to the power 2x plus 2x e to the power 2x, right? Y2 will be 2 e to the power 2x plus 2 e to the power 2x. This one I am doing 2 e to the power 2x plus 4x e to the power 2x, right? This will be this. Now y2, second derivative of y, minus 4 times y1 means 4 times e to the power 2x plus 2x e to the power 2x plus 4y. This is not 4, it's a 4y. I mean 4 times x time y means 4 times x time 2x. Here y2 I haven't put the value of y2, I just put it. Okay. So value will be 2 e to the power 2x plus 2 e to the power 2x means 4 e to the power 2x plus 4x e to the power 2x, right? Y2 value. That will be, see, 4 e to the power 2x and here it will be 4 e to the 2x, that will go. And then it will be having 4x e to the power 2x minus 8x e to the power 2x plus 4x e to the power 2x. So that is equal to 0. So you can show that when it's a repeated root, then if a m equal to, you have a, then e to the power ax and x e to the power ax, they are solution and they are linearly independent. Also what you can show that if m is equal to a up to n times you have, then e to the power ax, x e to the power ax up to x to the power n minus 1 into the power ax, there will be solution. They will be linearly independent solution. So that's why for y2, secondary for y, minus 4y1 plus 4y is equal to 0, the solution for this will be c1 e to the power 2x plus c2 times x e to the power 2x. That's why you get x, that x you get. That is a justification when it is you have repeated roots. So when you have repeated roots, that's why you get 1x extra, due to the fact that the vector space consisting of the set of all solutions of the nth order differential equation has dimension n. So in this case, the order of the differential equation is 2. So dimension of the vector space will be 2. What's the vector space? Vector space is the set of all solutions of this equation. And here we will get, if when the repeated root, you will get only one solution, mean only one function that cannot generate whole space, because that's, yeah, eventually you have one function, you cannot do that. So you need two functions. So when it's not repeated root, you will see the two different function, you will get two functions which are linearly independent. So that's why you can write c1 times that e to the power 1 root times x plus c2 e to the power another root times x. Or if there are many more root, you can write, but when you have repeated root, then you have to write like this. So if you have repeated root, like I told also, right, if you have 2 4 3 3, if you have like this, then what will be the solution? C1 times e to the power 2x plus c2 times e to the power 4x plus c3 times e to the power 3x plus c4 x times e to the power 3x. That x will come here. So if it is 3 3 3, one more will come, c5 times x square e to the power 3x. Let's keep, it's like that. Okay, again now we have 5 and 5, so the solution will be c6 e to the power 5x plus c6 x e to the 5x. That's all. That will be your solutions. I mean c7, of course. Yeah, you have 7 root. Then I mean this is, you have seventh order differential equation if you have, and the roots are like this, then the solution will be like this. Okay. So the question turns out, when it is a, what about complex roots? So you add this real roots which are distinct and repeated. So when you have complex roots, so I'll keep, let us keep this thing. So otherwise it will be theoretical mainly. So if you have R1, so M is equal to R1 and R2, where R1 is equal to A plus IB and R2 equal to A minus IB. So this we go get using E is equal to E to the power mx. right? So now R1 is a plus ib, so y1 solution will be y1, that will be corresponding to the power r1x, which will be to the power a plus ib, right? That implies e to the power ax time e to the power ib, that will be cos bx plus I sin bx. Okay, so y2 will be similarly e to the power ax cos bx minus I sin bx. Okay, so we can see that y1 plus y2 are two solutions. You can check that they are linearly independent also, and you can show that y1 plus y2 over 2 will be to the power ax times cos bx. Again, as we know, all of us know, if y1 and y2 are solutions, they are linearly independent or not, the addition of that 2 will be another also a solution. So y1 plus y2 over 2 will be also solution, and y1 minus y2 over 2y, that will be also solution e to the power ax sin bx. And you can check that they are also linearly independent. So how? So let's do it. It's cos bx e to the power ax sin bx. Now e to the power ax sin bx, right? My negative of sin bx plus a e to the power ax cos bx. And for this one, it will be b e to the power ax cos bx plus a e to the power ax sin bx. So we'll check that the Wronskian of this, whether it is 0 or not. So this will give you, so b times e to the power ax 2ax cos square bx plus a times e to the power 2ax sin bx cos bx minus of minus b e to the power ax, I mean 2ax sin square bx plus a e to the power 2ax sin bx cos bx. That implies b times e to the power 2ax cos square bx plus sin square bx will be 1 plus a e to the power 2ax, you have a e to the power 2x, right? Sin bx cos bx sin bx also same, so one is plus, another is minus, right? So that implies plus 0. So that implies b to the power 2x, which is never 0, not even at one point. So that implies they are linearly independent. I mean, e to the power ax cos bx and e to the power ax sin bx, they are linearly independent and they are solution. So any solution will be of the form a times e to the power ax cos bx plus b times e to the power ax sin bx, where you have to write a and b are arbitrary constant, a, b are arbitrary constants, and that implies e to the power ax. That's why we used to write e to the power ax times a cos bx. Yesterday I wrote about all this thing in the last class, but these are the justification of those. Okay, a and b are arbitrary constants. So when you have roots m is equal to a plus ib and a minus ib are the complex, you have complex root, then it will be like e to the power ax. The real part will come into the picture here, and the complex part will be here with some arbitrary constant a and b. Okay. Now, what about repeated roots? So similarly, when if you have repeated roots, you can write as this x cos bx. I mean x e to the power, of course, e to the power x e to the power ax cos bx, or x e to the power ax e to the power ax sine bx, they will be solutions. That also you can check. Similarly, we checked for the last one, we checked, right, for e to the power ax. So here also it will be like that. Okay. So yeah, last time we have discussed also, for the non-homogeneous differential equation, we have complementary function and a particular integral. You add it, that will be the general solution or the solution, usual solution for non-homogeneous linear differential equation. Okay, and the CF is nothing but the solution of homogeneous one. Okay, this will have arbitrary constant. So complementary function will contain uh, arbitrary constants, but particular integral will not contain any constants. So they are like one function only. The CF is family of functions in that sense. So PI means, we discussed yesterday, RHS over the, which acts on FD, the right hand side, left hand side operator, and this right hand side, right? Like it is by AX over, if you have D square plus 1, let's say A is not equal to 1, A is not equal to 1, then it will be e to the power AX, sorry, A is not equal to I. So it means, let's say A belongs to real number set of all, some any real number, then it will be x over a square plus 1, this will be square plus 1, which does not contain any arbitrary constants. Okay, so particular integral will not contain any arbitrary constant. And the solution, let's say y is equal to solution, the y minus pi will be the CF. So y minus pi will be the solution for the homogeneous differential equation. So among the all the nth order differential equation, one of our main focus is on second order differential equation, right? Second order linear differential equations. So how do you solve those? Okay, several ways are there, but yeah, okay, I think this second order, some other method to solve and find the solution is not included in the course. So there will be some reduction of order. So if you want to know like more, then those are like reduction of order, variation of parameters, so undetermined coefficient, all those things you can do. Okay, you can check if you want. So those will make the life little more easier. So other than, so whatever we have done till now are Cauchy Euler equation, but all the differential equation won't be of the type Cauchy Euler equation and constant coefficient one we have done. Okay, so all the differential equation in the real world application you won't get as Cauchy Euler equation, like very simple type, constant coefficient and all. So you may get different type of differential equations with varying, like not constant coefficient differential equation, which are having functions of different type. It's not in a very good form. Okay, so called good form. So then you have to approach in some other, you have to solve in different methods. So those methods are like this: variation of parameters, like I said, the undetermined coefficient, and reduction of orders. So all those things you can use. Okay, so there are many applications for the second order differential equation. Let's like motion of object hanging from a spring. So an object hanging from a spring with displacement d is given by and is modeled by the Hooke's law. You know, right? Hooke's law. What it say? So force F is the spring force will be equal to K times D. D is the displacement of the spring, like up to the natural length. This is the displacement from the spring to the natural length. And K is greater than 0 is spring constant, some constant. Okay. So then this F, you know, there will be many more things involved. I'm not going through all those things, but F will be kind of looking like M times A, right? And A is your d2x dt2. So second order differential equation will come into the picture in simple displacement array motion of to derive the motion of an object hanging from a spring. Okay, so differential equation of order 2 you can get there. Even in electrical circuits and many more examples are there where you can show that you can see the it is coming naturally. Okay, yeah. So and we have done also Euler equation, Cauchy Euler equation we have done also. So yeah, so I think most of the parts which are involved in this course are done. So there are some more things about maybe differential equation, maybe power series solution. So some power series solution, I would say that is one of the strong method to solve linear differential equations. Okay, one of the strong. So you can solve it easily. Let's say you have differential equation like y double. So y2 minus xy1 minus 2y is equal to 0. How do you solve it? This is not constant coefficient, it's not Cauchy Euler also. How do you solve these things? So for those you have other methods. Okay, so with this I will end the first part of the lecture. Okay, first part of the lecture, as I said, we will discuss a little bit about the differential equation. Okay, and in this part what we have discussed are how we get for the constant coefficient, how we can write that c1 times e to the power ax plus c2 times e to the bx, that two are constant coefficient, two are distinct real roots. And also we have seen if it is not distinct, if they are repeated also, then also we have uh, seen that how why we write c2 times x, x y it is coming into the picture, that also we have shown. And then complex root why it is coming into the ax time a cos a bx plus b sine x, that also we have shown. And we have seen some application, we have talked about some application like Hooke's law, where the second order differential equation will come into the picture very easily for a very simple physics experiment you can see. So there will be many more involving. Okay, yeah. So with this I will add the first part of the lecture, and then we'll start now the new one. I'm not new one, we have done already that part, that is mean value theorem, some problems, interesting problems from mean value theorem and Cauchy theorem. Okay, So we'll start with power series. Okay. So if you have a function fx, the power series at the function for the function f at a, you can write as fa plus f prime a over 1 factorial times x minus a plus I mean, it will keep on go. I mean, the thing what you will get is n equal to 0 to infinity nth derivative of f at a over n factorial times x minus a whole to the power n. Right? If f is infinitely, if f is, that has to be happened. Right? That has to happen. So f is infinitely differentiable. That has to happen because you are writing n equals 0 to infinity f nth derivative of f, so it means infinite times differentiable after also. But this thing, so some people might write always this in infinity f n a if it is always difference, but I mean x minus a whole to the power n. This is a series. This series may or may not be always equal to f at, I mean fx. Okay, so we'll give like let, if you have a if this type of terms are there, if they are converging to zero and also those conditions are there, then only it will be equal to fx. I mean, if this series might converge also, but still it won't converge to f, it may happen that it won't converge to fx. So that one example will show that it's not always that it is, if you have infinitely differentiable function, then also fx you may or may not write as a Taylor. You can write the Taylor series expansion of that function, but that may not be equal to always the function. Okay, so that's let's, if you have like this e to the power minus 1 by x square type of function, if I remember correctly, e to the power minus x square, fx equal to e to the power minus x square, and of course when x equal to 0 is not defined, so let's put it 0 and when x is not equal to 0. Right, so this is a function. You can show that this function is infinitely differentiable. How? So let's say what about first derivative f1 at 0. So let's say we want to find around 0. Okay, a is equal to 0 corresponding. Okay, so f1 0 will be limit as h tends to 0 f of 0 plus h minus f of 0 over h, that is equal to limit h tends to 0 e to the power minus 1 over h square, and f at 0 is 0, so that will be over h. Right, that implies, see now you can see when h tends to 0 this is going to 0, but e to the power minus 1 over h square will be f when h converts to 0, 1 over h square will converge to infinity. So e to the power minus 1 over h square will converge to 0. So it is now also it is in 0 by 0 form. But if you take derivative, so again it will be coming like this one will be 1, but this one if you take derivative, another h cube and all will come. So we'll rearrange it to make our life more easy, and you will see that will be 1 over h over it will become 1 over h square. You can see that both are now it is in infinity by infinity form, but more easy, a little bit more easier. H tends to 0. Now it you can write this is over h square. H to the power 1 over h square will give you minus 2 over h cube, right? Times e to the power 1 over h square. That implies limit as h tends to 0, h over e to the power 1 over h square. 1 over 2 also take common. Now this is in, so h is equal to 0, h it will be converging to 0, and e to the power 1 over h square will converge to, so it will be infinity, 1 over infinity. So it is 0 over infinity. When it is converging to 0 over infinity means 1 by infinity. This is going to 0 only. So 1 by infinity also converts to 0. So that implies half times 0 is 0. So we can show that similarly f2 at 0 will be also 0. F3 at 0 will be 0. I mean f at any n at 0 will be 0. So from the Taylor series expansion of the function, so what you can write, Taylor series expansion will be f0 plus f minus a, which is 0 times f dash 0 over 1 is we cannot be phenomenon, right? X minus 0 whole square f double plus 0 over 2 factorial. 2 factorial plus up to it will be 1 going. So that implies you have f0 will be 0 plus a time a dash 0 is x times 0 plus x square times 0, and it will keep on going. So what is what you get at the end is 0, right? The Taylor series expansion above 0 is 0, but your function is e to the power minus x 1 over x square when x is not equal to, when x is not equal to 0, x is not equal to 0, you get the Taylor series expansion of the function is 0. E to the power x square cannot be 0 when x is not equal to 0. So you cannot always write in this case fx equal to, you cannot write this not equal to the Taylor series expansion. Okay. So Taylor series expansion cannot always write Taylor series, but the meaning of that is Taylor series expansion is won't always converge to the function. Okay. So then where it is the function, then you can show that this function is finitely many times differentiable. Okay, that was from Taylor series. I'm doing the theory and some whatever we from week one mainly. Okay, next week 1. Taylor series and have value element. Okay. So now I want to use Taylor series expansion to do some inequality, some estimation. So what is that? So you can always write n times by 2 to the power n minus 1 less than 2 x to the power n minus y to the power n over x minus y is less than n times x to the power n minus 1 if 0 is less than y is less than x. For any positive number, on any positive real number, if one is less than another, then you can write this estimate. See, these type of things might be very useful. Sometimes I want to find out some inequality, find out bound something by some, maybe x minus y and x bounded. You want to bound x to the power n some other x to the power n minus y to the power n. So those time you may need is inequality. Okay. You have x to the power 7 minus y to the power 7. That will be less than equal to, and x y you know they are in some they are in a bounded domain. Okay. Then this will be less than equal to n times x to the power n minus 1 times x minus y. So what you can write that is less than equal to n times x to the power n minus 1, and this is diameter of this will be independent of the domain, independent of the this x y, which will be diameter of the domain. Let's say omega, bounded domain is omega. And if you know now only x is bounded, if x is bounded, you can show that x quantity is bounded. Or if you know want to know x to the power 7 minus y to the power 7 over x to the power 6, then that will be bounded in times diameter of domain. I mean estimating some for to estimate or to bound some term, you might need this type of inequality, this type of estimate also. So okay, so how you prove that? So to do that, let's say fx is equal to x to the power n. This is a polynomial, so it will be f is infinitely differentiable. Infinitely differentiable. Okay. That's very easy to solve. So now we take as y is less than x, we take Taylor series expansion around the interval on the interval y to x. Taylor series expansion on the interval y to x. So what will it will give you? See, if you expand the function, the Taylor series expansion on the interval y to x, so you can write that fx is equal to fy plus x minus y times f prime y plus x minus y whole square over 2 factorial f double prime y. So, and it will keep on going. In this case, the Taylor series expansion will be Taylor series expansion will converge to fx because of the continuously differentiable function, and you can write always like this. Okay. Also, Taylor series expansion about this point, what you can write is fx. So that implies x to the power n will be y to the power n plus x minus y times f prime y. What will f prime y? That will be y times y, n times y to the power n minus 1. Right. So plus x minus y whole square over 2 factorial. See, also Taylor series expansion, if you want, you can write up to a certain term, up to, let's say, second order you want to take. So in that case, it will be, so let me write it clearly. Okay. So if you want to write this Taylor series expansion up to a certain point, then fx will be equal to fy plus x minus y. Let's say I want to write up to this term, f prime y plus x minus y whole square over 2 factorial f double prime. Some xi will be coming in that scenario. So xi belongs to y to x. Right. So this over 2 factorial f double prime xi then in that scenario. So that implies it will be x to the power n minus y to the power n over x minus y, right, over x minus y will be is equal to n y to the power n minus 1 plus x minus y over 2 factorial times f double prime xi. So what is x minus y? Y is greater than x, right? Sorry, y is less than x, so that implies x minus y will be positive. Now what about f double prime xi? So f prime is f is n x to the power n, so it will be n times n minus 1 times xi to the power n minus 2. Now you see xi belongs to y to x, and y x all are positive, so xi is positive. So xi to the power n minus 2 will be also positive. So that implies the x minus y over 2 factorial f double prime xi, that is positive. That implies x to the power n minus y to the power n over x minus y will be strictly greater than n times y to the power n minus 1. See, one part you have shown, the first part. N y to the power n minus 1 is less than equal to x to the power n minus y to the power n over x minus y will be less than, will be greater than n times y to the power n minus 1. Okay. You can show in the similar way to show that the other way also, x to the power n minus y to the power n over x minus y. Show this homework. Otherwise, approach me. I will just tell you how to do that. If you have any issue, x to the power n minus 1, n times x to the power n minus 1. So combining these two, you can show the required estimate. You can prove the required estimate. Yeah. Now let's move to the next question. The question is, let f from 0 1 to set of all real numbers, set of real numbers be differentiable, and f of half is half, and 0 strictly less than alpha. Alpha is a number which belongs to 0 to 1. Suppose that f prime x is less than alpha for all x belongs to 0 to 1. Then show that fx will be strictly less than 1 for all x belongs to 0. If you have properties like f is a differentiable function, and somehow you get to know that f prime x is less than a number which is strictly less than 1, the modulus of f prime x, then you can show that the function itself is less than 1. Well, any value like it takes will be of modulus less than equal to 1, less than 1, not equal to less than 1. Okay. How do you prove that using, let's say, Taylor's theorem or mean value theorem, whatever you want, you can use. But how do you show that that is true? Okay, so let's do that. What is mean value theorem anyway? So mean value theorem, we have talked about mean value theorem. It's different for a differentiable function. Mean value theorem will hold, and it will fold between any 2 points. Let's say I want to take 2 points, like, because I know at 1 point value is 1 point value I know. So what was the mean value theorem anyway? Let us recall. Fb minus Fa over b minus a will be a point xi which is between b to a if b is greater than a. Otherwise you take the other way around. Okay, that implies modulus of fb here. Okay, not right. B is equal to x and a is equal to half. Okay, and then it has to be, b has to be greater than a. I mean x is greater than half. So in this case we are now. Okay, so then what will happen? F x minus f half over x minus half will be f prime xi, where xi belongs to x to half. But what about this f prime xi is less than 1? Modulus of that is less than 1. That implies fx minus f half over x minus half will be less than 1. That implies fx minus f half is half. That is less than x minus half, right? Now you know x is strictly greater than 2, half. So that implies fx minus half will be less than x minus half. That implies fx will be less than half plus x minus half, half minus x plus half. That implies 1 minus x will be less than fx less than x. And you know x is less than, sorry, x is greater than half, right? X is greater than half. But x is you are taking from the domain, so it has to be less than 1, and it is less than half. So from here what you can write, x is less than 1 you have already, so minus x will be less than minus half minus 1. So that implies 0 will be less than 1 minus x less than half, right? So from here what you get, fx will be greater than 1 minus x, which is greater than 0, and this is fx is less than x, which is less than 1. So fx mod in this case is less than 1 when, what is the assumption here? X is greater than half. When x is greater than half, of course greater than half, and then x is of course less than 1, that less than equal to 1, right? So from here we can show that for when x belongs to half to 1, that interval, then fx is less than 1. But what about the points, what about x belongs to 0 to half, or 0 less than equal to x less than equal to half? So then we take the interval as x and half. Okay, and we do again same thing. So f half minus fx over half minus x will be equal to some f prime xi, which xi belongs to x to half. But whatever is that, that is modulus of, if you take modulus of f half minus fx, that will be less than 1 times half minus x, because half is bigger than x now here, so half minus x. That implies fx will be less than half plus half minus x, and yeah, half minus half plus x. That implies x will be less than fx less than 1 minus x, right? But if you see here, x is greater than half, right? Sorry, x is less than half and it is greater than 0. What we want to know, what about 1 minus x? So minus x will be less than half, sorry, less than 0, greater than minus half. So 1 minus x less than 1. So thus fx will be less than 1, greater than 0. So hence fx will be always less than 1 for all x belongs to 0 to 1. So if any point in the domain, the modulus of the function fx will be modulus of the function f will be less than, strictly less than 1 for all x. Okay, so that's what we need. I mean, that's the question is asking. So the it was asking that, and it was asking to prove that the modulus of the function is strictly less than 1 if you know f of half is half, and f prime of x, f prime, the first derivative of f, is strictly less than alpha. Okay, so yeah, that's all for this question. Now the question is, use MBT to prove 1 minus x square over 2 factorial is less than cos x when x is not equal to 0. So how do you prove this one? Like 1 minus x square over 2 factorial is less than cos x. So these are some bound, maybe you feel is not useful for now, but it will be useful later when you do some estimate where you need cos x to be bounded by some, like bounded below by some polynomial. See, 1 minus x square over 2 factorial is a polynomial. So cos x, if you want to bound the cos x function uh, by a polynomial, and that bound is lower bound, let's say you require, then you can use this inequality. But how do we prove that? Using mean value theorem, which you know. Okay, so for that, what we do, let's say fx is equal to, we take fx is equal to cos x minus 1 minus x square over 2 factorial. Okay, then what you can show that, then what you can write that, if you can show that some, if how fx is greater than 0, then you are done. Now what is f0 is, let's say, what is f0? F0 will be 1 minus 1 minus 0, which is 0. So then I use mean value theorem when fx minus f0 over x minus 0 is equal to f prime xi. I will take two cases. One is x is greater than 0. Okay, x is greater than 0, then it will be xi belongs to 0 to x. X is positive number. That implies fx minus f0 will be 0. So if fx minus f0 is fx minus 0, that is fx. So fx will be equal to x time f prime xi, right? What is f prime xi? Let's first evaluate what is f prime x. F prime x will be cos x, derivative of cos x will be minus sin x, and derivative of 1 will be 0. Derivative of x square over 2 factorial means x square by 2 is equal to x. So f prime x will be x minus sin x. So f prime is whatever f prime xi, so xi minus sin xi. What about x? X is positive always. What about xi minus sin xi? If you uh, draw the sin x function and x function, you will see sin 0 is 0, sin pi is 0. So this is, it will be like this, and this will keep on going. But it will never go beyond x. X will be x. This is y is equal to x. This y is equal to sin x. X will be always greater than sin x when x is greater than 0. Right? So xi minus sin xi is greater than 0 as xi is greater than 0, because xi belongs to 0 to x interval. So xi has to be greater than 0, strictly greater than 0. So thus what you can show that fx is greater than 0 when x greater than 0, right? So we still haven't done the part like case 2. We are yet to done case 2. What is in the case 2? We will have x is less than 0. Again do the same thing. So fx, f, then in that case f0 minus fx over 0 minus x will be equal to f prime xi 1, some other xi 1, which is xi 1 belongs to x to 0, right? X to 0, because x is less than 0, x is a negative number. Now we know, all of us know that f0 is 0, f0 is 0, so 0 minus fx. So fx will be x time f prime xi 1, which is nothing but, we have already seen that, we have already checked the xi 1 minus sin xi 1. X is less than 0, and this quantity, draw the line. If you see, so it will be this type of sin x, y is equal to sin x, y is equal to x. So when x is less than 0, sin x minus x will be positive. So x minus sin x, I mean sin x function will be uh, sin x will be bigger when x is less than 0, right? That's why x minus sin x will be less than 0. So here xi is a negative number because xi belongs to x to 0. I mean xi is less than 0. So that's why this one will be also 0. So less than 0 and less than 0 will make fx is greater than 0. In here it was both positive. Here you have both negative, but the ultimate, you want fx which is positive. That's why you get fx is positive for all x belongs to, for all x, mainly for all x, which is not equal to 0. So even the this one, you can say that if it's f1 minus x square over 2 factorial is less, strictly less than, that's why the result when x is equal to 0, this will be equality. It's not a big deal. So this inequality, uh, you can write as equality, less than equal to for all x. But to be precise, when x is equal to 0 only, then only it is equal, otherwise it is strictly less than. That's why this x not equal to 0, to you have to prove f when x not equal to 0. Okay, and that's why the result is interesting. Okay, so most probably this will be the last question for this session. uh, the question is here. So I mean, the before that, so you can show that this is a example. You can show that x cube over 3 factorial will be less than sine x for x greater than 0. Okay, you can show that sine x will be less than x minus sine x minus x cube over 3 factorial will be less than sine x for x greater than 0. It's not true for x less than 0. Okay. Also, one question, cos y minus cos x will be strictly greater than equal to x minus y times sin x. How do you show that? This is for true for all x belongs to, sorry, xy belongs to pi over 2 and 3 pi over 2. Okay, so to do this, so we have to mainly take, let's say, take function fx is equal to cos x. Okay, so then what we can write, fy is equal to fx plus x minus y, sorry, x minus y times f prime x, right, plus uh, sorry, I think it will be y minus x, is not x minus y, right? Yeah, the Taylor series expansion, if you check it here, uh, x minus y times, yeah, so y minus x, it will be, yeah, y minus x. Y minus x time f prime x, and I will take up to second order. Okay, so y minus x whole square over 2 factorial f double prime some xi, and xi, then xi belongs to uh, xi belongs to x to y if y is bigger. Okay, so now fy, I mean, I'm assuming case 1 is x is greater than y. Case 1 is, sorry, x is, y is greater than x. Okay, case 1. So then this xi belongs to x comma y, that is valid. Now fy will be equal to then fx, what is fx is sin x, sorry, cos x, so fy will be cos y, that will be equal to cos x plus y minus x time, what is f prime x? If fx is equal to cos x, f prime x will be minus of sin x plus y minus x, y minus x whole square over 2 factorial minus of cos xi, right? Minus cos psi. Okay. So that implies cos of y minus cos of x will be equal to minus of sin x times y minus x will give you x minus y times sin x minus y minus x whole square over 2 factorial cos xi, right? Now x or y there in pi by 2 to 3 pi by 2. So xi also will be belongs to 3 pi by 2 to, I mean less than 3 pi by 2 greater than pi by 2. And what about cos xi then? Cos xi will be, say, what is cos function? Cos function at 0 it is 0, at, sorry, at 0 it is 1, at pi by 2 it is 0, and at pi it will be minus 1, at 3 pi by 2 it is, this is 3 pi by 2, it will be 0. Sorry, uh, this is at 5 by 2, this is pi at pi it is minus 1, is then pi plus pi by 2, it will be 0, right? So cos xi will be belongs to 0 to, not 0 to, yeah, 0 to minus 1, right? 0 to minus 1, because pi by 2 to 3 pi by 2, because pi by 2 to 3 pi by 2, so it will be cos xi belongs to minus xi to xi. So cos xi is less than 0, so minus cos xi will be positive, right? And less than 1. So minus cos xi is positive, and y minus x square, so y minus x whole square over 2 minus cos xi, right? That will be positive, because y minus x square anyway it is positive. Cos xi minus cos xi is positive, this will be positive. So if this is positive from this, let's say 1, let's say 2, injecting 2 into 1, we get uh, cos y minus cos x is greater than x minus y times sin x, right? X minus y times sin, this last one is strictly greater than 0, so that's why we get, and hence you prove. Okay, with this I will finish today's class. So thank you for uh, attending the classes. All the last few classes where I don't see people, but yeah, I saw up to like last maybe 9-10 classes if you were there. And yeah, thank you, and let me know if you have any doubt uh, after maybe in the YouTube if I post it, and otherwise you can send me mail also. uh, yeah, it was nice to teach you all guys. Okay, thank you for your attention.